So, with chapter 6, the reactions of alkenes. I won't go too much in detail because the class is a little bit scanty. So, we'll just briefly talk about it and see what it is. So, last semester and last week we talked a little bit about alkenes, their nomenclature, and their physical properties. Okay. Now, before we move into the mechanism of an electrophilic addition reaction, I want to remind you a little bit of the physical properties of alkenes. Okay, just a brief reminder of physical properties of alkenes. You know, alkenes are these molecules with a carbon-carbon double bond. That's what alkenes are. And what you need to understand here is that the carbon-carbon double bond is an unsaturated bond, okay, and means that there is possibility for that bond to become saturated. That's one thing. Then secondly is that at the level of the double bond, meaning that area, the area circle, that's an electron-rich area. Does that make sense? That's an electron-rich area because of the pi bond, those pi electrons. It makes that region rich in electrons. Now the question is, if that region is rich in electron, what do you expect? Say that again. Okay, chances are that if you are rich in electron, you will easily donate those electrons. That's true. What else do you expect when something is rich in electron? It will be attracted by what? By an electrophile, right? Does that make sense? Because the electrophile is positively charged. So, by electron deficient molecule. So, chances are that if you take an electron rich and then put it in an area, vicinity of electron deficiency, chances are that they will combine together. Does that make sense? And that's what is basically happening here. So, the whole chemistry of alkene, we will center it around the two sp2 carbons, meaning the sp2 carbons that forms the double bond. That's where the chemistry of alkene is. So we'll be looking at the reactions that takes place within that bond. Okay? And we'll have to understand the mechanism. So the mechanism is basically a logical explanation of how products are formed. Okay, it's a logical explanation. And during that mechanism, we'll have to look at some rules. There are some rules that will favor one mechanism over the other. And so that's your duty to be able to understand those rules. Okay? And those rules, you apply them according to the structure you have in front of you. So when you look at the structure, you say, okay, which rule we apply here? Which kind of mechanism will work best for this structure based on the features you have on the molecule. Does that make sense? Now, alkanes mostly undergo addition reaction. They mostly undergo addition reaction. And the reaction is specific. It is an electrophilic addition reaction, meaning that you are simply adding an electrophile onto the double bond. Does that make sense? Adding the electrophile onto the double bond. And so the mechanism for that electrophilic addition reaction is illustrated below. We talked about, before we go to the detail of the mechanism, let's remind ourselves. The arrow, when you're writing the mechanism, we talked about what the arrow means. Okay? The arrow always starts from an electron rich and ends up on an electron deficient. That's what I call positive. Does that make sense? That's what you guys need to keep in mind. So the arrow always starts from an electron rich to an electron deficient. The arrow can start from a bond. If the bond is electron rich, it can start from a lone pair of electrons. If that lone pair of electron is the electron rich center. And then it will end on the positive end of a molecule, which could be a bond or an atom. Is that okay? Now, this is a general mechanism for the electrophilic addition reaction of alkane. In this case, our electrophile is a hydrogen bonded on the bromine. So, this is our nucleophile, which is the alkene. And then the electrophile, E, is that particular hydrogen bonded onto bromine. And so the first step of the mechanism is that the electrons from the pi bond, take note, the electron from the pi bond will migrate and move towards the hydrogen, okay? That will in turn cause the bond between hydrogen and bromine to break. So the two electrons involved in the bond between hydrogen and bromine, they will separate and then go homolytically to the bromine. Does that make sense? And I want you guys to be able to picture that. So when that happens, two things can take place. Okay, the hydrogen gets connected to one of the carbons. You notice that this hydrogen here connects to one of the carbon. And so when it connects to one of the carbon, the other carbon becomes electron deficient. That's why we have a positive charge on the other carbon here. Does that make sense? And the last step now is the connection of the bromine onto that positive charge in order to have our addition product. Now the intermediate of this reaction is called a carbocation. That's the intermediate of the reaction. It's called a carbocation. So a carbocation is a species with it's a carbon species with a positive charge. That's what we refer to as a carbocation. Okay, that's the intermediate of the reaction. Question? Any question? Yes. Say that again. Full head arrows indicating movement of two electrons. Okay. Henceforth, most of the reaction, if not all of the reaction we'll be talking about, will be full head arrows. Okay. Meaning two electrons are moving at a time. So it'll be interesting to understand this mechanism. Most of the time when you understand this mechanism, things get a little bit easier. You know, you can easily predict the product. When I give you two things, if you know which one is a nucleophile, you know which one is an electrophile, then you should be able to guess what the product will most likely be. All electrophilic addition reactions have some features in common. First thing is that the pi bond is broken. Okay, so that's the first thing you will see. The pi bond is broken. And then you will have an electrophile. Take note, when we had the first example, HBr, I didn't call HBr the electrophile. I said the electrophile was the hydrogen bonded to the bromine. Does that make sense? It's not HBr. So if you are going back to this example here, my electrophile is not HBr. My electrophile is the hydrogen. So that's why the arrow stops at the hydrogen. The arrow does not stop on the HBr molecule. Does that make sense? And how do I know that the hydrogen is the electrophile in HBr? That's something you guys need to be able to do, right? I have HBr. How do I know that hydrogen is the electrophile in HBr? We did that. 301. 301. Why is hydrogen the electrophile? Say that again. Partial bonded. I want a better word. Because bromine is more electronegative. Does that make sense? Because bromine is more electronegative. And so you expect bromine to be partially negative and hydrogen to be partially positive. So that's what makes that hydrogen the electrophile. And so if the pi bond is electron rich, that electron rich will now attack that partially positive end. Does that make sense? So multiple choice. If I ask you what is the electrophile, take note, it's not the whole molecule. It's a portion of that molecule that acts as the electrophile. Does that make sense? Okay, and so the features of electrophilic addition, we have breaking of the pi bonds. Then we need to be able to identify what our electrophile is. And so the electrophile will add on one of the carbon and the nucleophile will add on the other carbon. And the sp2 carbons now becomes sp3 carbons. Does that make sense? All electrophilic addition are like that. All of them are like that. The sp2 becomes sp3. Let's think about the addition of hydrogen halide. meaning HX, okay? When we talk of hydrogen halide, that simply mean HX. X could be chlorine, it could be bromine, it could be iodine. Sometimes I need to learn how to write. So addition of halide. So we have first example over here, okay? So we have our double bond, and what we're simply doing onto that double bond is we're adding HBr. The hydrogen goes on one carbon and then the bromine goes on the other carbon. Does that make sense? Then on the second example is the addition of HI. The hydrogen goes on one carbon, which is not shown, so technically there's a hydrogen there. And then the iodine go on the other carbon. Okay, you guys should do the mechanism. I want to see the mechanism for that. Try to propose a mechanism for those two additions. Choose whichever one you like and do the mechanism. Try to propose a mechanism for those additions. Yes, if I say mechanism, then I need to see that intermediate. Yes. Whichever one, with HBr or HI, either reaction 1 or reaction 2. I just want to say mechanism for any of those. Okay? Just practice the mechanism for any of those. Choose the one you think is easier for you. While you guys are doing the mechanism, there's a question I'm expecting from you guys, but I haven't received the question yet. So, yeah, there's a question I'm expecting from you guys. I haven't received the question. So, while you guys are doing the mechanism, think about that question and ask me. No, not yet. It's not yet which one is more stable. It's not that question. But technically, it has to do with that question somehow. Yes, what's the question here? That's the question I was expecting. That's the question I was expecting. Huh? How do you know which one goes with which? Yes, you're basically answering the question. You see, but you guys are doing it now. I don't even need to teach you guys again. Truly. How do we know which one goes with which? And then she answer it, which one is more stable. Basically, those are the answer to the question, but we'll make things clearer. Does that make sense? So look at that molecule. The hydrogen connects to one of the carbon, and the iodine connects to the other carbon. Okay? Now, which carbon gets the iodine? Which carbon gets the hydrogen? In this particular case, it doesn't matter. Does that make sense? In these two cases, it doesn't matter. Why does it not matter in these two cases? Because the molecule is symmetrical. They are exactly the same. Does that make sense? So that's why it doesn't matter in this case. And so in the future, we'll see now cases where there's no symmetry, and we'll talk about the rules that govern the selectivity. And that rule will have to do with what she just said, stability. Does that make sense? And that's basically everything about these addition reactions of alkane. That's basically it. Okay? And so if you did that mechanism correctly, I will do the second one. If we did the mechanism correctly, so we'll have a HI. So the electron starts from the double bond and then ends on the hydrogen. The electron between the hydrogen and the iodine breaks and goes up to the iodine. So when that happens, you form an intermediate with a positive charge and a hydrogen connected over there, plus your iodine with a negative charge. Does that make sense? Now the iodine with a negative charge goes and attacks that positive center for you to have your final product. Does that make sense? Those are the steps of the mechanism. Before you sleep tonight, write this mechanism 5 times. Write it 5 times before you sleep tonight. Then if you forget, change my name. Does that make sense? If you do that, like you write it 5 times before you sleep, and then the next morning, if you forget how to, if you have forgotten or you forget, oh my God, English, then you change my name, okay? Then you change my name. That was the question, right? Which sp2 carbon gets the hydrogen? That's basically the question that Jakira asked. And we'll eventually answer it. So look at this example here. Let's look at this example, this molecule. You see that among on that carbon-carbon double bond, it's no longer symmetrical. That carbon-carbon double bond is no longer symmetrical. Does that make sense? I want you guys to show me the mechanism again. Let's do, because I told you guys to write a mechanism 5 times today. No, not now. After this class, you will write it 5 times before you sleep. So if you sleep at midnight, so by 11:30 you start writing it. Propose. I want you guys again to propose a mechanism for this. Propose a mechanism for that. Do it, okay? That's the way we'll do it. I want you guys to propose a mechanism and then look at the intermediate critically. Okay? Make a critical look at the intermediate when you propose a mechanism. Remember, you have 2 products. Let's call this product A, the third butyl chloride, and the isobutyl chloride, let's call that product B. So propose a mechanism that will lead to the formation of product A, and then propose a mechanism that will lead to the formation of product B. And take a time, put a break, look at those intermediates very well. Look at them very well. And then you will be able to tell me a story on your own without me even teaching you. Are we good, guys? So let's see. Let's look at that, okay? No, first thing. Have you proposed a mechanism that will lead to A and B? Now, have you looked at the intermediate? Look at your intermediate. Can somebody tell me something about your intermediate before I draw my own mechanism? More, I need more details. More details. Yes.
The 2 intermediates are different because for product A, you're going to get that citric carbon, that tertiary one is going to be have the plus charge on it, and then for product B, it's going to be
that N carbon.
Yeah.
Do you see that? Look at the intermediates. Okay, let me do the mechanism that will lead to product A. Okay, if you do the mechanism that will lead to product A, this is what you will have as an intermediate. Does that make sense? Do you guys have this as intermediate for product A? Who does not know? Who doesn't know? Yes.
So the substitution, that's a double bond going to carbon.
Say that again.
Is that a double bond in the speech?
No. Sorry, it's a single bond. I told you I need to learn how to write like that. So do you guys have this one as intermediate for product A? Everyone? Okay. Now let's do the intermediate for product B, okay? The intermediate for product B, you will have a CH3, a carbon, a CH3, H, a C, and a plus there, H2. Yes.
So the intermediate, why don't we have, like in the last example, we had, that, and then we had plus the iodine.
Well, no, I didn't show the full mechanism. I just drew the structures of the intermediate without showing the plus iodine. Because I'm only looking at the carbocation intermediate. Does that make sense? No. Okay. What she's asking is, I could add the iodine minus there, right? Add it. Well, in this case, it will be chlorine minus. Yeah, that's not our area of focus. That's why I didn't add it. But if you add it, that's fine. Okay, there's no problem with that. Is that okay? If you add it, that's fine. So these are the two intermediates I want you guys to have: the red and the blue intermediate. Okay. Now, question: when you look at those intermediates, what can you guys tell me? Is the blue, the red one is more stable, right? Intermediate red is more stable. Why is the intermediate red more stable? It's a tertiary carbocation. Does that make sense? Intermediate A is a tertiary carbocation, whereas intermediate B is a primary carbocation. So now you guys can tell me which of these products, A or B, will be the major product. Okay, so chances are that product A would be the major product of this reaction. Does that make sense? That's the way I want you guys to think about this problem. That's the way I want you guys to think about it. Okay? This is what I want you guys to think about it. So product A would be the more stable or the major product because it goes through a stable intermediate, which is a tertiary carbocation. Does that make sense? It's a tertiary carbocation. And this is a law. And this law, we call that a Markovnikov. I don't even know how to spell his name. I'm not Russian. Markov. I don't know how to spell it. So if I don't know how to spell it, read your textbook. Markovnikov. We call it the Markovnikov's rule. Does that make sense? What we just discussed is called the Markovnikov rule. And so the easier way, the way I always remember the rule is that for those who have more, more shall be given. You remember that verse in the Bible? Those who have more, more shall be given. Does that make sense? That's the Markovnikov rules. For those who have more, more shall be given. In this case, the more is the hydrogen. The carbon atom with more hydrogen will end up having more hydrogen. Does that make sense? And so if you look at structure A, let's look at the reactant. Let's understand Markovnikov's rule. Let's look at the reactant. We have two carbon atoms. Carbon atom 1 and carbon atom 2. Carbon atom number 2 has more hydrogen. Does that make sense? We have 2 hydrogens and carbon atom 1 with 0 hydrogen. According to Markovnikov rule, because carbon atom 2 has more hydrogen, it will end up with more hydrogen. And so if you look at the product here, this is carbon 1 and that's carbon 2. And you notice that carbon 2 now ends up with 3 hydrogens. Does that make sense? That's the Markovnikov rule. To those who have more, more shall be given. And that rule is based on the stability of the carbocation. Does that make sense? Yeah, that's just how organic chemistry is. And so everything we have discussed is here, summarized on that slide. Yes, Leslie. Well, structure B. Let's draw which out in this one here. Huh? This in my intermediate, that one. Yeah, I needed to show it. I needed to actually show because that hydrogen is the one that comes from HCl, you know. So I want to show to keep track of what I'm doing. Does that make sense? It's embedded in one of these CH3s. So whatever we've discussed, is here. Does that make sense? Everything you guys have discussed, everything we talked about is here. But just that the labeling of their carbon is a little bit reversed from what we did. The way they label it, they say carbon 1 is the one with 2 hydrogen, and then carbon 2 is the other one. And so when you follow this mechanism here, you end up having this intermediate, which is a tertiary carbocation. That's the one that will lead to product A. And then if you follow this route, it leads to a primary carbocation that will lead to product B. And you see they say that product B will not be formed. But we said it will be the minor, okay? Product B will not be formed because it goes through a primary carbocation. Product A will be preferentially be formed because it goes through a formation of a tertiary carbocation. That's the Markovnikov rule. To those who have more shall be given. Are we good up to this point? See how nice and easy chemistry is? And you can do it on your own without me even. Right, Zan? Yeah. And so again, we just talked about those carbocation. We just talked about those carbocation. Okay, let's remind ourselves. And then the stability of the carbocation is very similar to the one we talked about when we're looking at radicals. Okay, a tertiary carbocation is more stable than a secondary, which is more stable than a primary, which is more stable than a methyl carbocation. That's it. Okay, that's something we know. That's something we already know. We're just reminding ourselves about it again. And so, if you think about it, if I want to compare, let's do it again, okay? If I want to compare between these carbocations, carbocation A, carbocation B. I have two carbocations, A and B. Which one is more stable? A is more stable, right? A is called the benzylic carbocation, and B is called the allylic carbocation, just as we say allylic radical. So that is the allylic carbocation versus the benzylic carbocation. And so the benzylic carbocation is more stable. Why is the benzylic carbocation more stable? Same reason. Why? Can anyone remember? 301. Anyone? Can anyone remember? Resonance. Is that okay? It's resonance. Structure A can undergo several resonance structures. You can have several resonance structures with the benzylic. Remember, the more resonance structure, the more stable. Does that make sense? More resonance structure, the more stable. Before I continue talking about the stability of those carbocations, before we continue talking, I want you guys to propose the product of the following reaction. What would be the product of that reaction? Take note, the reaction will take place around this bond here. This is the double bond that's of interest. That's where the reaction will take place, around that double bond there. So what would be the product? So ignore the ring, okay? The ring will only help us to decide, but the reaction doesn't take place on the ring. It takes place around that double bond. So what do you think the product would be? What do you think the product would be? Two products. I will draw both of them and you will choose the best one. The blue or the red? Oh, yeah, it's correct. Okay, the red one, right? We all with the red. Does that make sense? We all understand why. Does that make sense, guys? You can use Markovnikov, and you can use the stability of the carbocation to be able to say that the red will be the major product. Is that okay? Now, in terms of stability of carbocation, let's go back again and mention it briefly here again. For the primary, secondary, and tertiary carbocation, just like we talked about in the chemistry of radicals, okay, we said the tertiary carbocation was more stable because of what we refer to as hyperconjugation. You know, remember the carbon atoms are a little bit electronegative. And so those carbon atoms, when you are surrounded by 3 carbon atoms, just like what we discussed in the enema, you remember, when you are surrounded by 3 carbon atoms, they tend to send electrons towards you. They tend to give you electron. And so that tendency of giving electron is what we refer to as hyperconjugation. Okay? So I don't want you guys to overthink about it. So that hyperconjugation is a tendency of giving the electrons. And so by giving those electrons towards this positive charge, you are kind of stabilizing it. So the more carbon atom surrounds a positive charge, the more stable that positive charge is. That's why a tertiary is more stable than a secondary, which is more stable than a primary. Does that make sense? That phenomenon is referred to as a hyperconjugation. We won't go into more detail on hyperconjugation. So hyperconjugation and resonance, they all have to do with electron movement. Does that make sense? And so what you guys should generalize is that the more you can cause an electron to move, the more stable that structure will be. So that electron can move through hyperconjugation in case of primary, secondary, and tertiary carbocation, or the electrons can move in terms of resonance, in terms of benzylic, allylic. Does that make sense? And now, which one do you think is a greater contributing factor? Hyperconjugation or resonance? Which one do you think would be a greater contributing factor? Which one? Resonance. Does that make sense? Yeah, so resonance has a stronger power, a stronger contributing factor than hyperconjugation. That's why the benzylic and the allylic are more stable than the tertiary, primary, or secondary. Does that make sense? Yeah. So that's the way I want you guys to think about this kind of stuff. That's the way. Okay, let's stop here. I think I'm good. I don't need to penalize those who came and left. Okay, I think we are good here. We'll continue from where we stopped next class.